to day 2 of the UW-Stork seminar series given by Professor Paterson from Cambridge University. One of the requirements that Gilbert put into his request was that the awardee not be given a, quote, crappy plaque. And so I went on a search for something that wasn't a crappy plaque, and I found this at Tiffany.
So maybe some of you
recognize the famous blue bag of Tiffany. On your graduate student salaries, I'm sure you're giving each other different gifts.
So,
Tiffany had this thing advertised that was called a pyramid. But it didn't look like a pyramid to me. It looked like the more appropriate tetrahedron. So I called them up and I said, does it have 4 sides or 5 sides? Does it have a square base or a triangular base? And she said, well, it has a triangular base. I said, yes, it's a tetrahedron. Call it a tetrahedron, not a pyramid. You'll sell more of them to organic chemists. So, this is the inaugural Gilbert Stork lecture, and I think that this will be the memento that we give to all succeeding Gilbert Stork lectures as well, so that this trinket will become recognized and coveted and will occupy places of honor in all the recipients' homes or offices.
so when I got this, and I just set it up here
to avoid, I was wearing white gloves a little while ago, so you see me in a suit and a tie and wearing white gloves, you might think of another career for me, but I wanted not to put fingerprints on this, and it occurred to me that this looked an awful lot like the cover of the Dark Side of the Moon album by Pink Floyd. And as it turns out, the late Sid Barrett was a citizen of Cambridge, and so you can see that we have a little light show here. And in fact, it reminded me of being at a Pink Floyd concert in Camp Randall Stadium with 80,000 crazed Pink Floyd fans a number of years ago.
So, you can see this photograph that we took is of the award, and it has this inscription, and this will be the only one that says inaugural Gilbert Stork lecture. This will do.
So, this photograph you saw yesterday, this is Gilbert Stork, and this is Sam McElvain, his PhD advisor. One of the things you might not notice is if you read the brochure, you can do the math. Gilbert arrived in Madison in 1942 and earned his PhD in 1945. So a 3-year PhD, which is pretty impressive in any area. Running too fast here. Okay, so I just wanted to list some of the awards that both Gilbert and Ian have accrued in their careers. And I'll point out that Gilbert Stork won the award in pure chemistry, which is the top ACS award given to a young chemist. That was in 1957. I'll just march forward 40 years. He was given an honorary doctorate from the University of Wisconsin. Some of the other notable things I'll point out is that at age 39, Gilbert was elected to the National Academy of Sciences. That's a very young age to be inducted in the National Academy. You can see that For almost 50 years, he has been collecting the top prizes in the world associated with chemistry. You can see that he got the award in chemical sciences from the National Academy. He has won many honorary doctorates. You can see that he's a recipient of the Roger Adams Award, the Lowell Prize, which is often considered to be a predecessor to a Nobel Prize award. And he won the Derek Barton Medal recently from the Royal Society and the C. Brown Award and the ACS Award. So, along his illustrious career, and as I said yesterday, we are the very happy beneficiaries of Gilbert's generosity endowing this lectureship that we'll have every year. So, Ian Paterson similarly has won many awards, and I should point out that he is just recently won the Royal Society's National Product Chemistry Award, the Tilden Prize. He is a fellow of the Royal Society of Edinburgh, a fellow of the Royal Society, FRS, is what it's commonly called, and a variety of other awards from academics and industry. Interestingly, he has trained over 80 PhD students, postdoctoral co-workers, has over 250 scientific publications, and you can see that he has given more than 400 lectures around the world describing his research. So with that, I want to introduce Ian again, and he's going to tell us about a fascinating story on structure determination and synthesis of the Spirastrellolides.
Okay, thank you very much, Steve, and good afternoon, everyone. So hello again to those of you who were in my lecture yesterday, and those of you who've got better things to do and didn't come to my second lecture, well, I don't blame you. Anyway, so let me move on and introduce my second topic, and to do so, I'll switch over and try and find my talk. Should be here. Right. Okay, so today will be a little bit different. My introduction in terms of, let's say, saying very nice things about Gilbert, I could easily repeat that, but I'll just really sort of summarize it in one slide. That Gilbert, back at Columbia, early this year, obviously very much enjoying chemistry, enjoying meeting up with visitors, and also, importantly, looking back not only on his amazing achievements in science, but his training of organic chemists over the years. So this particular T-shirt is actually the front of the T-shirt, which is a memento of the Stork Symposium back at Columbia when Gilbert turned, I guess, about 70 back in 1992. So here, this is the lineup of the speakers. I guess there's about 8 of them. And really these are sort of famous names of people who worked with Gilbert, either doing a PhD or postdocs. But in the background, there are more than 300 names, probably about 320, of, again, students and postdocs that worked with Gilbert. And as I mentioned yesterday, approximately a third of those, which is well over 100, have gone into academic jobs. And if you extrapolate from that, what that means is over 100 people worked with Gilbert, a large number of people would have worked with those 100 people, so you have propagation, and really a very large number of people are in the Stork family, if not Stork group. So this is just an incredible contribution to science and the science of organic synthesis. Okay, so I'm going to move on. And what I kind of want to share with you this afternoon is, first of all, I want to make it nice and relaxed. So we're going to go to a Caribbean island, Tobago. This is one of the nicest beaches I've ever been on. So it's Pigeon Point, Tobago. And so this wasn't necessarily just a vacation, but I try to get as close as possible to the location of the source of this class of natural products, which I'm going to describe the synthesis of, which is coral reef, not too far away from this point, probably about 50 miles out in this direction. Now, in terms of the source of the Spirastrellolides, I have to introduce this particular sponge. So this sponge is sort of bright red in color, and in terms of size, well, it's not really necessarily such a big sponge. It's actually reasonably common and it's Caribbean wide. It does have some predators, so it's not just natural product chemists looking to identify some interesting structures which may have some useful biological activity, but these turtles, hawk-billed turtles, essentially like to munch their way through many things, and one of those many things is this particular sponge here. So if you read this, so one of the samples of Spirastrellolides in Bahia contained a volume of this sponge that suggested the entire specimen was consumed at once. So these things are hungry, and this is part of the prey. Okay, so what can you find in Spirastrellolides? A range of natural products, but one particular class which I think is really quite unique. And in terms of, let's say, a synthetic chemist, one that really one would consider a beautiful structure. And so these things appeared in the literature, first of all, back in 2003, isolated by Ray Anderson's group at UBC in Canada. And the initial structure, which appeared in JAX, is here on the right-hand side. And so what we have is sort of a macrocyclic lactone, spiracetal, peptidopyran, acid side chain with a couple of double bonds here, and lots of wiggly lines. So an interesting structure, but a real problem of stereochemical elucidation. So if you're going to start a synthesis, what on earth should you begin to make? Anyway, we started the synthesis probably soon after this paper came out, and thought maybe we sort of work on the bottom bit, and progressively, maybe the rest of the structure would be revealed as Ray Anderson maybe isolated more material, could do more NMR work, and maybe could actually get crystalline derivative and obtain an X-ray sample, X-ray crystal structure. Okay, so in terms of activity, it's pretty potent. It's this low nanomolar activity is an antimitotic agent. It's really very scarce, and so estimated more than 2 milligrams is tough. In terms of mechanisms of action, it's quite different from the compounds I talked about yesterday. Spirastrellolides are protein phosphatase inhibitors, and particularly are active against protein phosphatase 2A. So there's some similarity with some other natural products like oligonucleotides, nucleic acids. So this compound, of course, attracted our attention, and not surprisingly, many other synthetic groups said, wow, this would be a really nice project to work on for various reasons. First of all, there's uncertainty over the structure. Secondly, it's very biologically active. And thirdly, maybe we can get some funding. Probably it's in that reverse order. So, other synthetic contributions in the States, Jeff Vervander, Craig Forsyth, Richard Sung, UW-Madison, Amy Smith, Andy Phillips, and someone who I sort of compete with from time to time, but he certainly has a lot more funding than me, is Alice Berschner from Germany. So this structure got our attention, and we started to think about, well, how can we put it together, and how can we determine the stereochemistry that synthesis progresses. But after about a year, so 2003, 2004, there's another paper that came out from Anderson's group, which provided more information on the biological activity, but also reassigned the structure. And so the revised structure is really quite different. So in the top part of the molecule, this D Spirastrellolides becomes this Spirastrellolides, so DEF ring system. There's this thing that gets hydroxyl group here that gets replaced by chlorine, and essentially then you still have the same side chain. But because they managed to isolate more material and did a lot more NMR experiments, progressively they could assign some of the stereochemistry. So some of these big lines now have been replaced by relative stereochemistry. But with this structure, there is actually still something like 16 possible stereochemical permutations. Because from the NMR analysis, one could assign stereochemistry blocks. This block here, this block here, this block here, and this block here. But relating those stereo clusters together is actually quite challenging. So the Spirastrellolide is the acid, but what's actually isolated and purified, and in terms of activity, it's pretty much the same as the acid, is the methyl ester. So it's in fact methyl ester and isolated. Okay, so if you look more carefully then, so there's these color-coded regions, the blue regions are starting to design, the green regions are starting to design red, and this sort of pinkish color on the side chain. All together then, what we have is a situation where there's still 16 possible stereoisomers to consider for synthesis. So in the top piece, this Spirastrellolide, really an unusual structure, benefiting, of course, from stabilization from the anomeric effect, and also having this chlorination here, 698. And all the systems are vectorial. With the bottom Spirastrellolide unsaturated DC, again, if you look at it, this benefits from stabilization without the anomeric effect. So in terms of synthesis, this is going to help. And again, all the systems are vectorial. So the relative stereochemistry, as I said, between those four highlighted regions was initially unassigned. So what do we do in terms of considering synthesis? Well, ultimately, we want to go after the whole molecule, but progressively, maybe we could try and make some fragments and see if the NMR data for those fragments agree with that for the natural products. And if we put, let's say, stereo clusters together, maybe one combination relative to another one or other possibilities matches the NMR data better. So progressively then one might build up a much better picture of what the structure of Spirastrellolide actually is. Okay, so this is very much early days. This would be certainly 10 years ago. Our initial synthetic dynamic. So here's the structure, and we have macroscopic electrons, close this on some stage. We would build in the side chains with undefined stereocenter, and obviously one can make either enantiomer or selectively. And we build this then by some kind of stilly kind of cross coupling. The bottom piece, what we didn't know initially, was the relationship of this stereo cluster here, including the Spirastrellolide, relative to this cis-substitute tetrahydroquinone A ring. So maybe we should go after the two possible permutations and see if one has a closer match to the NMR data. Bearing in mind, of course, that what you'd be doing is you'd be comparing something which is half the structure with something which, in the natural product, is conformationally much more organized through having the macrocyclic skeleton. So, who knows what would come in terms of doing that comparison. So for the top piece, which is going to become the DEF rank, you probably go after something like this tetracyclic lactone, and maybe this shows you our level of synthetic planning. We would say 625, 626 carbon-carbon bond formation. So it doesn't really reveal too much about how we're actually going to do it, but somehow we have to think of a way of connecting the bottom piece with the top piece. Okay, so let's maybe do this, and unravel it a little bit further. So we're going to get two possible permutations of A-ring stereochemistry relative to all the stereochemistry in the region. So if you unravel the C-ring and sort of stretch it out and think, well, probably we have to put some protective groups on. Well, we don't like protective groups, but they are necessary to assemble something like this. And what we saw is some relationships of stereocenter patterns, which might help us in terms of thinking how we could sort of build in the appropriate carbon-oxygen skeleton at the same time as controlling the necessary stereochemistry. And so this Z-alkene would come from an alkyne composition, carbon and aluminum reduction. So kind of stretching and unravel it. So break that bond, we've got alkyne, this one should be anti-diacetyl, and maybe if we cleave that, get back to the A-ring, we've got two stereocenters, and we could control this center from that center using chemistry which we discussed yesterday. This part of the molecule, 1, 2, 3, 4, 5 bigger stereocenters. 4 of the stereocenters of oxygen. When we think about starting with a carbohydrate, but we don't really do that kind of construction. It's not to say that it wouldn't be a good way of doing it. So we thought probably we could start with something like this, which is of course from tartrate. Okay, so that's enough in terms of basic retrosynthetic analysis. Let's kick off the synthetic effort. So kicking off the synthetic effort, two next steps. Hold of this, hold of the scale. So slightly modified validation, instead of using the usual ICC, it's another monoterpene carry, which actually gives you primary sense in the product. So do the alylation, treatment base, oxymicro, cis, ring, selectivity. And then we can kind of go in two directions, taking advantage of the pseudo-symmetry of that cis by substitute tetrahydropyran, and do some manipulation on one side and some manipulation on the other side. So this direction here, we cleave the double bond, we do another acetylation, that stands to the three direction. And then a few fairly straightforward steps then gets you to this C1, C-aldehyde, C1aldehyde with three defined stereocenters. And what we want to do is to get other permutation where essentially that stereocenter stays the same, but we grab these two relative to that one. So you can go from this common intermediate with 4 steps so that kind of switch it over essentially. C1 becomes C1 here, and this becomes aldehyde. Do the alylation, sal connection, ozonolysis. That gets you here, and now mentally turn that over, it gets into that. So without too much effort made these two initial C1 C11 subunits. Now we can set C11 stereocenter using this ketone, and this particular ketone, if you just rely on, say, the cyclones boron inlay will give you maybe in such a situation about 10 to 1 selectivity, which is reasonable, but one can reinforce that selectivity with higher ligands. Here we actually use the seaborne chloride. That gives pretty much exclusively the 1,4 take advantage of this center and see a reduction to anti-reduction with diol, and then a few steps involves saccharide, knocking off this benzyl group, going to the aldehyde, changing to give the corresponding alkyne. So we made this. And started out this one as well. So this epi relative to this one made this. With the aldehyde for the alkyne addition, we started out tartrate, making this aldehyde again, asymmetric methylation. This is now, say, back in 2004, two steps to this, using some chemistry to describe the context of our synthesis of bleodermatoline. This lactate-derived ethyl ketone, making boron enolate. We actually have very highly selective anti-aldo addition that controls the serotonin C3, So a little bit more manipulation to its cleavage. Gets you here, hydrogen oxidize, again, gets to the aldehyde. So we made another fragment. Wow, making fragments, start to join them together. And so joining them together, lithium, adding into this aldehyde, oxidizing, lin-log, gets you to enol. Now, I mentioned yesterday that at the end of the synthesis, particularly if you're a reasonably complex polyketone, you have to get the protecting groups off. But in this case, you also have to get the protecting groups off at the initial stage and sort of figure out what we make. And what we try to do is take off the protecting groups in sort of stepwise manner. But that didn't really work that well. So we actually stripped off all the protecting groups of HF nitrile, knocked off TDSs, and two acetonides, TDS as well. So this one was cyclized up to give this C1 to C5. And we did it with the other alkyne fragment here, which is epimeric here, there, gives you this. So these two, of course, by initially in the Mars spectrum, are very similar. If you look at them carefully and compare, particularly the proton spectrum relative to that region of the product, you begin to start to gamble. One of them maybe fits a little bit better than the other. So here are the two possibilities again. And what we found, so this comparison with particular region of Spirastrellolide, expanding region C7, C9 here as well. If we were going to put money on it, in other words, or maybe just toss a coin, we can think to ourselves that in terms of the better match, the one which is better is some unit here. So therefore, we put all our effort into progressing the synthesis based on this stereochemistry. So I emphasize that gives you maybe a hint of what the relative configuration is, but we don't have a clue of what the absolute configuration is at this time. What we consider doing, trying to figure out what the absolute configuration was, is maybe we could do some kind of collaboration with Anderson. And what we proposed to Ray was the following. While we can make these sort of fragments of the hemisphere, or we could probably go after some northern hemisphere, and maybe sort of simplify that back to structures like this. So the question was, did he have enough Spirastrellolide A to be able to do some degradation? So at the time, he actually managed to degrade a lot of Spirastrellolide A by simply trying to make various derivatives to get something hopefully crystalline X-ray. But he did have a little bit of lag. So he agreed that he would take his sample of Spirastrellolide A on his semester, set him on paper one by this bismuth dial, this is the oxygen cleavage. And if that happened, then some kind of reductive work should give fragments like this. So if we therefore, by synthesis, go after this, with either these two up or these two down, maybe we can actually correlate the degradation fragment, and that would give us a much better idea of what the stereochemistry is of the bottom part of the molecule. Okay, so on the synthesis side, kind of all we have to do is step back a bit, and instead of having all of this stuff off here, we just need to truncate it a little bit. So again, unravel these species by acetal, same idea, alkyl aldehyde, appreciated here now, similar relationship between this oxygen. And so we derive from this aldehyde, either simpler aldehyde, which is the stereocenter. So we now really wanted to have a better synthesis of this piece. And what we started out with then was not to do the brown annihilation, but instead really very scalable chemistry using Eric and Jacobson's excellent hydrolytic connection resolution method to get this oxide building block on large scale, Grignard opening, across the Paterson Stork now the stereocenter set as we did before, oxy-Michael, reduce, oxidize. And now because we found from that initial NMR comparison that the more probable relative stereochemistry bottom piece shown here, then we don't actually have to do asymmetric annihilation, take advantage of substrate control. So now there's chelation control containing allyl-silane, and the allyl cleave gets us into reasonable selectivity. So again, repeat chiral addition, and goes through to this point here, and again, quite similar, building up the alkyne from the dipole alkene gets us through to this. So in comparison with the first generation approach to that fragment, this is much more scalable, so you can make multi-gram quantities of this without huge effort. Okay, so now we take this, and we take this simpler aldehyde piece and do the same chemistry again, going through this enone. Now we want to remove this PMB ether, but keep the silane protecting groups on it. We do that with DDQ, nicely closes up to give this, and then finally we actually remove the silane protecting groups to get fragment A. So we made this, and we made corresponding compound where these two hydrogens are down. And then we sent them to Ray Anderson and hope that we get an answer back. The answer back was, we're trying to do this degradation. We couldn't fish out anything sensible. Even having your authentic samples of these fragments so that we could sort of look for what we need, we didn't actually manage to find the same compounds in a sort of degradation mixture. Okay, so we didn't really make any progress here, except we had better synthesis of this fragment. Okay, so let's go back to the plans. I've talked about this. What I haven't really talked about is I'm going to sample this. So this is definitely the most challenging part of Spirastrellolide synthesis. So highly oxygenated, you have to put chlorine in, you have to go through configuration of acetal carbons, and you have to have scalable synthesis. realistically, what we need grand quantities to be able to go forward to try and connect fragments together. Okay, so our initial idea was some kind of mentally take carbonyl, maybe do this by an HWE hydroid. So that would give you kind of something. This piece is a bicyclic fragment called stereocenter. And the corresponding phosphonate bit would be this, which is called stereocenters. So we need to make this, we have to sort of join together, and then hope maybe to this. So the guy who worked on this particular fragment was Olivier, and his full-time job is at Syngenta, and he managed to persuade Syngenta to come and work in my lab for a year. I thought that was great. But they had a very good reason for doing it other than he enjoyed chemistry, is that Olivier previously worked with Novartis in Basel on the Discodermalide project. And one of my students was on the Discodermalide project funded by Novartis, so she spent some time in Basel. The two of them got together. So I think Olivier's main reason for coming back to my group is so he could spend a lot more time with his girlfriend. Actually now he's his wife, so it's kind of a very happy ending. Anyway, that's a digression. Okay. So Olivier quite liked Paterson. Do this. It's not great. The mixture isomers, so 1. We can sort that out next steps. Sharpness isolation. Importantly, you actually get E. And with the Z isomer, of course, a diastereomer. And so chromatographically, you can separate the major diastereomer, which is one here, from the unwanted minor one. So take us through the first one, aldehyde here, so the ground correlation. So sets those two stereocenters, and then actually quite tricky chemistry here. What we do is knock off, oxidize ketone first. That particular stereocenter, of course, is quite delicate because the double bond conjugation. Careful here. So oxidize the ketone, knock off the test. That then closes onto the ketone and methanoid forms mixed acetal, and then finally leave the double bond to the aldehyde. So it gets through to this, preserve that stereocenter. Okay, another piece make. So we start with a simple aldehyde, take advantage of the brand procedure, which was developed subsequently to Ohlschlager. Instead of having a methyl group, chlorine essentially works through quite nicely. Chlorylation set the relative and absolute configuration here. Good selectivity. So methylene, now we have this chloride, and you can do a dihydroxylation again. Now if you do dihydroxylation without a chiral ligand, just what's been 10 peroxide NMO, you get a useful level of substrate selectivity about 4 to 1, 5 to 1 in the anti-sense. What you would expect if you had, let's say, hydroxyl or alkoxy group, same constants on chlorine there. But if you do it with a ligand system, so sharp, very good selectivity. A few steps, there's aldehyde, elaborate through this phosphonate. Now it's bearing hydroxide procedure, which I described yesterday, gets the corresponding enol, and the Stryker reduction. So in my lab, I'm enjoying, and of course working very hard, as a postdoc with Gilbert. There are various key people, Eiichi Nakamura, who I mentioned yesterday, who currently is in Cambridge giving a lecture while I'm here, and Jeff Stryker, who is now at Alberta, Canada. So Jeff's chemistry in a way that caused us to look at this copper hydride procedure, clean ways of producing enols to saturated ketone.
Okay, so maybe this would be a suitable precursor
to give the top piece of this bis-bioacetal DNF ring system, the co-oxygenation, and of course including chlorine. Well, the initial results were frustrating. So if you treat this thing with acid, you find not to hydrolyze this up, all you manage to do is to destroy stereocenters, go from this to furans, bad news. If we play very hard in various conditions, eventually after some considerable effort, with acidic conditions, 7 degrees centigrade, certain optimal period of time, exactly how long, and on a good day, and importantly on a small scale, we got 40% yield of this system here. The NMR analysis of this, NOEs, and the proton chemical Paterson spirastrellolides gave us confidence that yes, this does actually correspond to the region of spirastrellolide. Again, we don't know the absolute configuration. So we could make this in a few milligrams. This was really a serious early stage bottleneck. As we tried to scale it up, yield went down. So we had a good problem. How are we going to make this particular fragment or something close to that fragment? I mean, useful scale, so gram quantities. Okay, so now there was a very important development. Seven, 3 years about the project. So found out we can do quite well. Found things we can't do that well. We found things we can't do at all. And so another conjugate spirastrellolide B, lacking the double bond, the C-ring system was isolated by Ray Anderson. And again, they could make various derivatives of this, and one of them they made was and also another difference is the chlorine here spirastrellolide A. Now they could do a little bit of degradation, so oxidative the side chain and converted C4 to this power phenyl ester. This thing, and it did some damage to this part of the molecule, so the cyanide dropped off and got oxidation to the ketone. This pretty much still looks like spirastrellolide. It's crystalline, and so they got crystal structure. And the good news was that all of this relative configuration corresponded to what they had in that second paper in organic letters, and also corresponded to what we deduced in terms of building up some permutations of stereochemistry at the bottom of the relationship of that technology to those stereocenters corresponded to what subunit 1. But the really good news was the absolute configuration corresponded to the series we were working in. So we didn't have to go back to the beginning and sort of swap everything else, swap everything for the enantiomeric starting material or enantiomeric chiral reagent. Okay, so 2007, maybe it was time for a commercial break. Here we are punting again. So maybe we're back at the design stage. Back at the design stage, at least in my group, usually involves a trip to the pub. Usually on Friday evening, usually with a pad of paper and a pen, and we sort of sketch up ideas, and we sort of revise our synthesis, have another beer, revise our synthesis, and eventually come up with what we think is our best possible route. So after that revision, we have what's called strategy evolution. Does sound grand. What we wanted to do now was we knew what stereochemistry had been building up. But what we didn't know is what's the best way of connecting the top piece with the bottom of this line. So this is like undefined carbon bond formation. So if we unravel this, chop the side chain, stretch this out of it, where maybe this could come. So we knew that we could do this BC spirastrellolization, particularly if you had PMB ethers here that work quite nicely with DDQ. And we could probably keep all the other protective groups on, with the exception of this one. And we had various ideas how we could connect the bottom piece with the top piece. Our kind of best ideas, main bets, were those were two possible strategies. Some kind of Julia olefination, hydrogenation, make C25, C26, or alternatively, maybe this could be a double bond, or C24, C25, and maybe then we could do some kind of actually C23, C24. So we can mentally imagine retrosynthetically dehydrating this double bond. So you have a double bond there, single bond there. Maybe we could do a Suzuki coupling here to make that bond and some kind of hydroboration to introduce those two stereocenters. So those were our main ideas. We didn't know which is going to be better, so we of course have to pursue both of them. So what we needed then was various fragments. So this sulfone to explore the Julia coupling strategy. This vinyl iodide, the Suzuki hydroboration alternative. We had a good synthesis of this now. We can produce some multigram quantities. Some missing component was how on earth do you get this DEF, bispiracetal, and get it on scale. So almost certainly went to the pub again, beer, felt very hard. We've been trying much too hard over building up. Let's try and simplify. So if we simplify, so if you unravel this, notice that these oxygens are going to come into a dihydroxylation, open up the acetal, maybe this ketone, this alkene, we could do a double asymmetric dihydroxylation. Actually a little bit of acid, magically it would zip up and give us the required compound. So where this would come from is, okay, we have to make that carbon bond, so aldehyde, ketone, some kind of either HWE or aldol, dehydration, etc. And what we found from preliminary studies is yes, if you have this little chloride, then Sharpless works extremely well. 93 to anti-relationship here. What we found previously as well, with this system, you can use BZ mixture, you get very high E for this. So if you used essentially the same ligand system, but do both double bonds and do perhaps a lot more useful chemistry in one pot. So to make this aldehyde, this deconjugated aldehyde, this lactone, lactate-derived phenolate again, aldol addition, salylation, cleavage back to this, and gives this. This is now changing the oxidation state. This, which was previously TBS ether, now we're going to have it as ketal, acetal, so that using chloralylation reaction, methylation gives you this, and this can be done on a multi-gram scale. And how these can be united, or an aldol reaction, easily eliminated with spiral reduction. What we had to do at this point was reduce the ketone to the alcohol knock off the DBS, and importantly to double oxidation like sperm to any cyclization of this diketone. Now call on Professor Sharpless to work his magic. Maybe this could be converted to this. Of course, I wouldn't be presenting this. I wouldn't finish Spirastrellolides if this key reaction did not work so well. So in fact, this thing, using standard AD condition, what you fish out initially is this system here, so it's like cyclic mixture there, so NMR is not great, but it certainly is the oxygenation. And now you touch this, a little bit mild acid, ethanol, give us the DEF, the NMR analysis, and so all the stereochemistry correct, so essentially all these bonds configuration. You get some hydrogen steroid relative to that stereocenter there. After silation of that mixture, hydrogen steroids separated, we equilibrated under acidity levels, so build up grand quantities of this intermediate. So what had previously been a serious bottleneck now opens up completely. You get useful quantities of this key fragment. And then just selectively knocking off Paterson and oxidizing to the aldehyde. Okay, so now we have a root of this. How do we make this? Explore one for C26. So look at the Julia complementary strategy first, which I think is the first explored. So let's stay back. Pressure, alkylation, system here, anti-steric context, manipulation of aldehyde, so heavily glycolate, aldol, fructose, allyl conjugate, take advantage of PMB for ketone using methylation, knock off this, gives you this, methylation, then methylation, alcohol. This one is sulfide, and that is the appropriate Julia chemistry. So we can make this, but of course there's quite a few steps, Trying to do the carbon bond forming reaction, Julia modifying Julia conditions, is really very disappointing. The best we could get, probably on small scale, about 30% yield. The problem here is this aldehyde really very hindered. It's called this spirastrellolides. Also got delicate, so you don't recover second reactive stability. You either get the desired compound, so 40% yield, and everything else is junk. So this is again bottleneck. So even though we got some material forward, what we do with it is selective hydration here, and then a reduction of the small internal double bond, and then the S bond. This is actually what we want to make. Now, let's say limited resources. One realizes that it's going to be tough to bring material through if you've got 30% yield right in the middle. We didn't really like that at all. So what was the alternative? To explore this Suzuki coupling. And so to make vinyl iodide, firstly it's much quicker, 7 or 8 steps. Previously, methylation,
knockoff potassium gives this.
Three stereo
Centers,
double bond,
iodine.
Now,
Taking
aldehyde,
aldehyde,
methylation, now one part, combine it with
divine iodine will be accumulated in analysis conditions, useful descent conditions.
now the yield,
was one double realistic times the yield relative to the alternative Julia
so we
coupling.
could build in,
So we could build in double bond, make one common bond.
now we've got
Territory,
because if
this
this was the
other way around, so the
here,
group was here, there's a little stereo center, there's a lot of information, literature about the rest of it, what face that double bond should
so this kind of system,
So this kind of system where you can this run around, certainly is much less
so
slow.
therefore we made
Various
one fragments or goals,
Clear answer. Some of them gave one direction, some of them in the other direction. In many cases, they were based on just modestly pivoted.
but
But
in
practice,
here,
this system here,
it's an early stage,
it's an early stage, but this one so much better than that.
do it
Do the
high duration,
duration
phase,
phase,
and do that, double time.
double line duration. First one goes first,
Secondly, this one
secondly,
goes,
this one goes,
and
then
you show there we
silate
silate
to get out the Chris test of the third year.
and this
Correlated here was given from Julia coupling product. Stereochemistry used these two centers here. Those two centers were.
okay, so
Okay, so moving forward,
Suzuki
the Suzuki coupling wins the competition in terms of how we can connect
top
what
piece,
top piece.
we have
We have this fragment, we have this fragment,
this.
we have this, and we start to put things together.
Okay, so put things
Okay, so
together.
put things together. Primary test ether, you can knock off mild acidic conditions, oxidize the
We
aldehyde.
have this
We
alkyne.
have this alkyne, lithium, add it to the aldehyde, linear hydrogen, oxidize here.
PMB,
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 DQ,
DQ, all things should zip up and give the BC spiracetal there.
and does indeed.
Does indeed, so you form the BC spiracetal.
But
Unexpectedly,
we lost
He lost the test ether.
this one here.
this one here
Came off.
came off cleanly.
So
So
the student who did this,
student did this,
really,
He was really keen to stick that test ether back on.
I persuaded them.
I persuaded him and said,
Ultimately, got to get
ultimately, you're going to protect it off, and why not take advantage of it, drop it off,
more
to
than
achieve
one thing.
more than one thing,
Transformation.
transformation.
Maybe the system.
Maybe the system is also telling us something that it doesn't want to have a protected there. So let's all fall free alcohol.
So we could get this. So we
we get this, now this is C1, this is C4 case, so it's looking like Spirastrellolide.
And very important,
And very importantly, of course,
Building up fragments together, if you're going after something like one of these large macrocycles, you have to build cyclides.
And this was
And this was
almost unbelievable.
almost unbelievable.
It's our first
Because our first attempt at
macrolactation, the right oxidation state is acid
I
alcohol.
think was the
This, I think, was their first attempt,
Really
room temperature, not doing anything special. This thing cyclized amazingly. Give this, and we had a very nice and spectrum.
So we can make,
So we can make 38 member macrolide core.
however,
However,
we had to think about how to build a side chain.
And what we would like to have
What we would like to have done was selectively TBS ether and grow the side chain here and eventually move on to protected groups.
we couldn't do that. We could not. It seems like very simple transformation to selectively leave that TBS ether. That TBS ether
It's actually quite
is
It's
actually
actually quite a private position, probably to some extent.
it's
Very
very
difficult. It's macrocycle, held over it.
do.
all we
So all
could
we
do
can
is
do
really just knock
is
off
really just knock off all the protecting groups.
Doing so,
doing
Doing
so.
so,
first
intermediate synthesis, we've got something which is highly crystalline,
X-ray,
and we've got X-ray.
so this is
So this is the crystal structure now. So you can take it here.
It
It tells us several things.
Firstly,
all of the stereotypes.
all of the stereochemistry which we thought we put in turned out to be correct, so it's always nice to show confirmation. And it also has this fairly
highly
kind of highly organized counter bond network connecting up the hydroxyl groups with their oxygen, suggests those dashed arrows.
Okay, so
Okay, so back to planning. What we need to do is building this whole side chain. We take the macrocyclic lactone.
we have to
Complete the synthesis by building all of this. So at least this looks like a relatively simple fragment.
and one can get hold of it
One can get
either
hold of
an
it,
enantiomer,
either an enantiomer, malic acid, or dimethyl ester, dimethyl and then this sort of selective process here, where what we do is first of all we take out this bromine reductively, and then replace that bromine with tin, then vinyl stannate, and then we topped off this thing and made the methyl ester, so we can make the enantiomer as well.
and then we practice the
And then we
chemistry.
practice the chemistry, so with our top piece, with our reasonable quantities of,
through to
we
this
could go through to this
carbonate,
lily carbonate, do silica with this, through this intermediate building the whole side chain.
of course,
And of course, one doesn't have to use this,
this,
one can use this, because we give the same intermediate, so either way, this one actually works out a bit better to give this.
so we can build it the side
So we
chain.
can build in the side chain on the top of the molecule, that whole macrocycle. Question is, can we extend that and get to work on the macrocycle layer? It's actually turned out quite hard.
Firstly, it's okay, we can knock off all the sound protecting. So what we have, first of all, is pentanol. And what we would like to do, but couldn't do it, would be a selective oxidation of primary alcohol to the aldehyde, just to leave all those hydroxyls unprotected. We could not do that. We're always oxidation in positions. So we have to put some things back on. So thiol is a acetaldehyde, diol is a acetaldehyde, and then we've got some mixed acetaldehyde there, we can knock that back to the alcohol. Then oxidize here to the aldehyde, since it's unprotected, and then do the fitting methylation to give you this. To do this cross-metathesis, we had to push it very hard. So 80 degrees benzene, and leave it for a reasonable amount of time to try and get a useful level of conversion. Never really went all the way. So what it was telling us again was really that alkene is now very hindered, because it's next door not just to DF with Spirastrellolides, but probably is held over the macrocycle, and one really has to push it very hard to make any of this alkene product. So we can now take this and do the power-state cross-coupling. And we did it with, separately, two experiments with this enantiomer, the R configuration and the S configuration. And the two products, even though that stereocenter, they draw it this way, it's a considerable way from that macrocycle.
Those two diastereomers by NMR are very different, because of course that side chain is held over the macrocycle, so it's in a chiral environment, which is in close proximity in terms of 3D. Now we can actually look at some of the NMR data for Anderson and found that this configuration corresponds to the bisaccharidide which he made from Spirastrellolides. Therefore, that was really good news. We'd essentially cracked the first synthesis of Spirastrellolide. And all we had to do was remove, now we all know we remove a couple of saccharides, as we did with methanol, gave us our first sample of synthetic Spirastrellolide in ethyl ester. But even at this time, slightly worryingly, when we made our first sample and ran the NMR spectrum, particularly the proton spectrum, there were really some differences relative to the published data. Of course, that's worrying. And when we ran it under maybe somewhat different conditions, the NMR changed a little bit as well. So to totally tie down with confidence that we had synthesized Spirastrellolide in ethyl ester, we need to get an authentic sample. So fortunately, Ray Anderson sent us an authentic sample. We ran the NMR. The NMR was standing a bit different from published NMR. What we had to do finally was to purify by HPLC the authentic sample, our sample, and run the NMR under identical conditions, and then they completely matched. So what that tells you is, even though we were at what we thought was the end of the synthesis, maybe subtly something strange was going on, and we didn't actually have the structure we thought we had. Anyway, so this is good news. Not only did we go to the pub for some beers, but of course we had a really nice party in the park. And so that was sort of now way back 2008, I think we finished our synthesis, and then we did a couple of full papers 2 years ago in OBC and various reviews. But maybe it's time to pause to think. Firstly, there's a whole family of Spirastrellolides. Maybe we could use this particular route to give not just Spirastrellolide A, but this is sort of a family of them, so B, C, D, E, F, G, H. We could probably make some other things. And maybe we could use this advanced intermediate, so pentanol macrocycle, and set on the table, we're going to get all the ones in red. Of course, we go forward and make animals. But that's actually a lot of work. And right about that time, this makes sense, all the people on cases, and I had new students starting. And actually very good students, very good students to project group already. So he wasn't quite sure he would do a PhD. So he left me and joined the management consultancy in England. And after about 3 months, I kind of stand this is boring. And I want to come back to PhD. Fortunately, I managed to get funding for a delay of a year in science PhD. And I thought, well, why don't we try and make Spirastrellolide in hopefully a more efficient manner? So commercial, this is actually a very nice pub. So those of you who've been to Cambridge, so Steve, I don't know if you ever taken for a drink at the Anchor, it's a pretty nice pub there on the river. Okay, so we're going to initial strategy evolution. This is strategy evolution 2 for second generation synthesis. Because we knew various things. First of all of the direct chemistry was reliably fine. So we didn't go to the process of trying to make some fragment comparisons and figure out what's correct. And then fragment how actually get to the end. So we can now be a lot more focused in our planning.
And what would be nice is, okay, cleave this open, unravel, and so really pretty much in the penultimate step, we would do a macro lactonization, some kind of texture can just knock off to get either the methyl ester or a free acid. So if you take this now, what we're doing is we're kind of inverting some of the order of steps. So we're pretty much building the whole carbon chain, then cyclize. Whereas what we did previously, we made a macrocycle, and had little few carbons hanging off the macrocycle, and tried to get into that end carbon to selectively oxidize, which we do the drops type Paterson is very challenging, getting conversion possible. So maybe we can do things better if we do it this way, make all of this and close. So now leaving this back, so a vinyl addition to this thing, which would then be a carbonate, so we do this panel stilly coupling again. The whole thing would fall apart, you lose CO2, and that would then reveal a hydroxyl here, which would close onto the carboxyl. So we practiced some of this chemistry first, so we had this, and so we do hydroge, which took off the benzyl group. I think I also took off that test group, and then we did cyclize through lactone, dival, vinyl grignard addition, cyclic carbonate. And yes, this actually works quite nicely, and we made perhaps an interesting analog of the top piece of Spirastrellolide. Right. So I think one thing which I stress doing this kind of synthesis is if you only have one student with no technicians in the German system, postdocs, that student has to keep cooking while he's eating. So you have to continuously replenish his stocks to advance fragments. They'll fall from all of us and move on and finish the synthesis. So he had to remake this, and do now the hydroboration of Suzuki coupling, and the yield is actually going up. Tricycle double bond, do the double hydroboration, with some optimization of pentamine selectivity, protect those two things as test ethers. Now we remove this test ether, without touching the other ones, really nickel off the benzyl ether to this, we have this tetrol. Now we do one pot kind of multiple oxidation, the top piece and the bottom piece. So this penfold oxidation works really very nicely. It's close enough to give the 5-member lingual lactone, takes C17 through the aldehyde. So we're sort of doing both things in one pot, so that's good. With the lithiated alkyne, the aldehyde didn't work well at all, for some 50 issues, this thing started to interfere. So I go for the lithium chromium, so it's an NH2 reaction, which works nicely, and make that one. Linbar oxidized here. So now compared to the first generation synthesis of the TBS ether here, this is lactone, PMB, and so we have to just touch it, heating review, things should cyclize up. So it does cyclize up as expected, but we got also traces of the heat protected C23 alcohol. So this time we're going to trace that. So we stopped the test group back on, and we sort of optimized it so we didn't lose anything else either. So we went forward with this material. So HF with TBS ether, early lactolactolactolactolactolactolactolactolactolactolactolactolactolactolactolactolactolactolactolactolactolactolactolactolactolactolactolactolactolactolactolactolactolactolactolactolactolactolactolactolactolactolactolactolactolactolactolactolactolactolactolactolactolactolactolactolactolactolactolactolactolactolactolactolactolactolactolactolactolactolactolactolactolactolactolactolactolactolactolactolactolactolactolactolactolactolactolactolactolactolactolactolactolactolactolactolactolactolactolactolactolactolactolactolactolactolactolactolactolactolactolactolactolactolactolactolactolactolactolactolactolactolactolactolactolactolactolact through this. Now, C1 oxidation through the aldehyde to the acid. Iron acidic comes really nicely, so the negative yields go up. And Phil Maltons, which is the guy who didn't want nitrogen control, even though it wasn't
motivated by prospects by salary, and enjoy organic chemistry, you can build up useful stocks of this particular advanced ingredient. So now on paper, on the slide, of course this hydroxyl has to be close to that hydroxyl, it's got to close. However, in practice, it's a disaster. So when we have this system here, tried many conditions for Yamaguchi or alternatives to Yamaguchi macroorganization, it was very hard, put up the benzene, did everything possible. We could not get any of this out at all. If we use the whole side chain, we got this, and we cannot make something of this, it could be strange. This one did not side at all. We never airway for this. Case of, well, red hair to white hair is no. That's the order of these things. So what on earth we're going to do to solve this problem? So let's look back at our first generation synthesis. In our first generation synthesis, through no real intention, we made that BC Spirastrellolide, that pesticides dropped off. The alcohol, this thing, actually after some optimization, cyclizes like green. So what we proposed was that this thing is constantly makes your organisms cyclize, but with this thing here, that pesticides is interfering with the molecule getting confirmation of cyclization. So it's really just sitting there and doing nothing for eventually be degraded. So fortunately, there's some limited time available, limited stocks. We did the obvious thing, which is now remove, first of all, this pesticides. Now, first attempt, cyclize is great news. Knock off both pesticides, cyclize is even better, really good news. And if we had enough material, we would have knocked off all the salary ethers, and pretty confident this was cyclized just as well. Also. Okay, so now what we've got to do is find the connection. So we take the theory of the salaries, methanolysis of this gives us that spirastrellolide methyl ester. So the good thing is that the second generation synthesis, students do one of these that all this that is actually done single, very clean hard student. Film all this, and the yield is now 6 times better than the first generation synthesis. But also told us in that first generation synthesis, without realizing that we were down the bucket. This was serendipity. And without that ether dropped off and saying, well, keep off, it would have caused probably a lot more effort to finally finish this. We know we finished it. Okay, so second generation synthesis, really good. And one take-home message that I'm going to give you from this lecture and from yesterday's lecture, this came to me on sabbatical in Melbourne, and as my cousin in summer, beer here. So this is called beer in the bar, and probably such a great part of the city. And so I looked out the window, and something screams out at me, who's this? Perseverance. So this is actually the name of a album. This looks like what it is. But you do this kind of complex model of synthesis, be it natural product or anything, not only to be very smart, experimental, but you've got to show, not just easy, perseverance to achieve so much. So that's the word that I leave with you, and I'm going to thank some people again. So these are all left my group. So Phil Maltus ended up in Lundberg, Denmark, and Anderson was just amazing postdoc. You move to the dark side. Goes over to Oxford, doing very well. Steve Dolby is going to industry in America, Raleigh in UK. John Lynn went back to Korea, SK Energy. Olivia found his wife in group. Christian was with Ross, Julian Pfizer. Collaborator as well, particularly Rangers, because without that authentic sample at the right time, we may not, well, it takes a long time to establish whether or not we actually done a synthesis. So these collaborators are actually more to do with other projects in my group. One guy who's been extremely helpful all times goes back to when we collaborated with Novartis on discodermalide. Stuart Mickle has sort of given me very useful starting materials and intermediates over the years. So this is pretty much my current group, and I probably want to thank Simon again for his contributions yesterday. Two more slides. First of all, again, commercial Cambridge, really very nice place, visit. So again, hunting the river. And final slide, really want to include this lecture and yesterday's lecture by saying this, of course, would be possible without the generous down Gilbert Stork. So finally, I thank Gilbert very much. Here's a very nice picture of him. Okay, so thank you very much.
I would like to first say that was there is almost a lot of position of natural products that account for Question from the audience.
So you must have some thoughts about what exactly that architecture hypothesis does in blocking the confirmation of the
Yeah, so I can obviously show the slide, we'll probably go through sections, so I can't just try and give it to you verbally. So with the crystal structure of that pentanol, it shows a very clear hydrogen bond network. And I think if you sort of open up the macrocycle, that kind of hydrogen bond network, if you have that free alcohol C23, can help bring two, let's say, arms of the molecule together to cause closure. But if you have a tax ether there, of course, that's not possible at all. And it may actually adopt quite a different conformation, which is unproductive for cyclization. We've done a reasonable amount of modeling of the cecoacid or something, approaching the cecoacid, trying to figure out what is the conformational possibilities of these systems with tax ether or not tax ether. But maybe this is the limits of modeling. We never got a clear result from the modeling, so it's more a case of thinking about hydrogen bonding and how that could be productive. Now, of course, in terms of biosynthesis, most likely what happens is the carbon-oxygen skeleton is built up, spiracetals are built up, tetrahydropyrite ring is built up. There's no protecting groups. That thing is conformationally organized so that for the sort of thioesterase cyclization step, no kind of enzyme to hold it, we probably don't even need it. It sort of cyclizes with no difficulty.
Ian, I had a question. It's kind of a philosophical question that has to do with a signature of your work with aldol chemistry, is that you have, rather than use chiral auxiliaries, which have been widely utilized for stereoselective aldols, you build your chiral auxiliary essentially as part of the molecule. Can you comment on that and how you came to that?
I think it was influenced by Gilbert, this sort of typical Stork approach. You start with one stereocenter and relay that stereochemical information to as many other as possible. The kind of history of this is kind of interesting. So first time I came across Rochester was when I was with Gilbert, but it didn't actually feature in the project I was working in. I think we probably tried to use it for something, or maybe it was to make a model to do some chemistry. And then, of course, the source of it was Clark Still, because Clark had used it in his Monensin synthesis, and he'd managed to get it from Roche. And so when I went back to Cambridge, I thought, it's potentially a very valuable starting material. And at that time, people, of course, had made the aldehyde, tried to do chemistry with the aldehyde, but the level of stereoinduction with that alpha-chiroaldehyde is not that great. So I guess our analysis was, well, why don't we look at the ketones and try and do aldol reactions with that and see if we can use that stereocenter, which essentially you buy, to control now 2 stereocenters. And just progressively we found, yes, we could do that, we could set those stereocenters. We'd get almost any permutation. We could do it with ethyl ketone, methyl ketone, alkoxy methyl ketone. So it's just very general and powerful. And as we used more and more elaborate aldehydes as the components, particularly if those aldehydes had some stereocenters in it already and maybe even got a bit crowded, the chemistry worked well. And then the next stage was, of course, well, we did play around with reagent control and IPC boron chloride. That's actually very useful, particularly if there's no high level of substrate-based stereoinduction, so use the chiral ligand. And in situations where you need to overturn substrate selectivity, very, very powerful and used in the Novartis synthesis of discodermalide as one of the late steps. And then the next evolution of it was to go from Rochester to lactate, and then that allowed us to do, well, maybe the equivalent of an Evans-Syn aldol, but for an anti-aldol. But we had this appendage, and as you say, that appendage is not really just a chiral auxiliary. We don't walk off. We use that chiral auxiliary to sort of build up more of the skeleton. So, I have to say it's a classical Gilbert-Stork approach, and that's his inspiration to me, or at least one of those inspirations.
Great, thank you. Other questions? If not, I'm going to lure Ian back here behind the podium to shake his hand in front of the Gilbert Stork Award. Thank you very much. It was fantastic.
Okay, so
And there is a reception. There is a reception in the Shane atrium starting now.